In this video, we're going to explore exponential functions. We're going to evaluate exponential functions. We're going to find the equation of an exponential function given a graph or some ordered pairs. We're going to use compound interest formulas. And lastly, we're going to evaluate exponential functions of base e. Now, if we were in the classroom, I'd have you group up and talk about all of this information right here. So I'm just going to talk about it instead since we're not in the classroom. And if we take a look at x squared and 2 raised to the x, with f of x, the exponent is a numeric value and the base or the variable is what we see as the base. And then over here, what I have is 2 is my base and my exponent is the variable. So if I were to start choosing values for x, so if I would have done f of, say, -2, I would have -2, the quantity squared. If I did g of -2, then I would have 2 raised to the -2. Well, f of -2 is going to be -2 multiplied by -2, which is 4. But g of -2, which is 2 raised to the -2, becomes 1 over 2 to the 2, which becomes 1 over 4. So when the base is a number, my exponent becomes the variable, and this is an exponential function. This is not an exponential function because of the fact the base is the variable and the exponent is always the same number, which is 2. So if you were to graph these two on the same xy plane, I'm just going to poorly graph this, y and x. My x squared would look something like this. We know that if I put in 1 or -1, 1 will come out. If I put in 2 or -2, 4 comes out, which is up here. And so I have a graph that looks something like this. So this is my f of x. Now, if I graph 2 raised to the x, well, 2 raised to the 0 is 1. Anything raised to the 0 power is 1 except for 0. If I put in 1 for the exponent, I get 2 out. But if I put a -1 to the exponent, I get 1/2 out. If I put in 3 for the exponent, well, that should be, yep. So if I put in 2 for the exponent, I get 2 out. That's cool. Or 4 out, which is, if I put in 2, I get, so if I put in f of 2, I get 4. And if I do g of 2, I get 2 to the 2, which is also 4. However, when I put in 3 for g, so g of 3, which is 2 to the 3, I give you the answer is 8. 2 to the 3, which is 8, f of 3 is 3 squared, which is 9. So they're different. And then 2g of 4 is going to be 2 to the 4th, and I get 16. And f of 4 is 2 to the 4th, so that also gives me 16. If I do g of 5, I'm going to get 32. That's 2 to the 5th, which is 32. However, f, erase that on f of 5 is 5 squared, and that's 25. So what ends up happening is that the exponential is going to grow faster, actually much faster than the squared. And when we're in the negative, it ends up going down close to the axes, because if you have f of -3, this is 2 raised to the -3, which is 1 over 8. And f of the -4 is going to be 2 to the -4, which is 1 over 16. So here's some basics that we need when we talk about exponentials. The first thing we need to talk about is percent. Percent change refers to the change based on a percent of the original amount. Okay. Exponential growth refers to an increase. And that is an increase that is a constant multiplicative rate of change over equal increments of time. That is a percent increase of the original amount of time. Exponential decay refers to a decrease. So when we say exponential decay, we are decreasing at a constant multiplicative rate of change over equal increments of time. That is a percent of decrease in the original amount of time. And you're like, what exactly does that mean? Well, so here's the thing. Let's let A be the initial amount. And we could be talking about anything. We could be talking about money. We can be talking about radioactive decay. So we're talking about the radioactivity of a element decreases because the decay means decreases. So we have some initial amount of some substance, whether it's money or something like that. Exponential functions are of this form. F of x is equal to a b raised to the x. That's where they always are. If I do f of 0, then I'm going to have a b to the 0, and b to the 0, as long as b is not 0, is just going to give me a. So at time equals 0, a is the initial amount, which makes total sense. Now let's assume that b is 2, and I like 2 because it's easy to work with. So if I have f of x is equal to a 2 raised to the x. A is the multiplier, it's the initial amount. In fact, it's actually the y part of the y-intercept. So if I have f of, say, negative 2, this becomes a 2 raised to the negative 2, which is a, and then it becomes 1 over 2 to make it a positive exponent, which means I have a times 1/4. F of negative 1 is a, and then 2 raised to the negative 1, which is a multiplied by 1 over 2, which is just a times 1 over 2. We know what f of 0 is. And then f of 1 is just a times 2 to the 1, which is 2a. And f of 2 is a times 2 squared, which is 4 multiplied by a. And you can see when we're talking about a percent increase is that when I put in negative 2, I got 1/4 of a. When I put in negative 1, I get 1/2 of a. And so what I'm doing is I'm multiplying this previous 1 by 2. So if I take 1/4 and multiply by 2, I get 1/2. If I take 1/2 and multiply by 2, I get 2 to the 1. If I take 2 to the 1, or 2a multiplied by 2, I'm going to get 4a. And that is that percent of increase. I'm increasing by the same amount, which is a percent increase, and it is 2. So we know this is increasing. Now, if I say f, let's do g this time. Let's do g of x is equal to a b raised to the negative x. Again, g of 0 is going to just be a b to the 0, which is still a. So you can see that these two will produce the same initial output when we're on the x is equal to 0. So then if I do the same thing, if I do g of negative 2, this is a, and again, we'll let b equal 2 to make consistency here. So we have 2 raised to the negative 2, and it's negative 2. So this becomes a times 2 squared, because double negatives make it positive, which gives us 4a. G of negative 1 is equal to a 2 raised to the negative 1, which is a times 2 to the 1, which is just 2a. G of 0, which we did, so we'll do g of 1 now. Let's do g of 1. This is going to be a multiplied by 2 negative 1, which is a 2 raised to the negative 1, which is 1/2 of a. And you can see this pattern will continue. So as x gets larger from negative 2 to negative 1 to 1, I'm actually dividing by a factor of 2 each time. And it's decreasing because I'm dividing by a factor of 2. So if my exponent is negative, I am dividing by that percent each time. And if my exponent is positive, I am multiplying by that percent each time. So that's what that is about. So does exponential functions increase at a constant rate? And the answer actually is no. And you're like, but you just said that we have a percent. Well, it's a percent increase or a percent decrease. It's not a constant rate. And you're like, but I'm always multiplying by 2. Yeah, so let's look at the two graphs. Or let's just look at one of the graphs of an exponential. Here's y and here's x. So let's just graph the exponential. Let's just graph f of x, which is equal to 2 to the x. It's going to go through this 0, 1. And if I were to put 2 points on the graph, so with this point, and then connect them with a line, and then I come over here and I do this point and connect them with a line, you can see that this line is a flatter line than this line, so the rate is not constant. So when we talk about an exponential function increasing at a constant rate, that's what we're talking about. It does grow at a rate that's proportional to its current value, which is growing at a rate of 2 times, or growing or decreasing at a rate of 2 times if the x is negative or the x is positive. So it does not have a constant rate of change, but it does grow proportional to its value. You're like, yeah, I don't get that yet. You will by the time we're done. So here's a couple of things that we need to know about exponential function. A that we have right here is the non-zeroable number, and it's called the initial value. And that's what happens, again, when we put in f of 0. F of 0 gives us a, b to the 0, which gives us a, the initial amount. That is the y part of the y-intercept. B can be any real number, and it has to be positive, any positive real number, and it can't be 1. And you're thinking, why can't it be 1? Well, because if I did f of x is equal to a 1 to the x, this is just going to give me a, no matter what I put in for x, it's just going to give me a, which is just a horizontal line, so that's not interesting. And you're like, why does it have to be positive? Well, say we had, as an example, g of x is equal to negative 2 raised to the x, where my base is negative. If I do g of 1, I'm going to get negative 2 to the 1, which is 2. Or negative, excuse me, it's going to be negative 2. If I do g of 2, I'm going to get negative 2 squared, which is 4. And you're thinking, okay, well, this seems to be increasing, because we know exponential functions will increase or decrease, always increase left to right, or always decrease left to right. So it's either always increasing or always decreasing. So let's do g of 3. Well, g of 3 is negative 2 to the third, which is negative 8. Oh, wait a minute. That's not always increasing, because I went from negative 2 to 4, but then I went back down to negative 8 as outputs. So that's not always increasing, nor is it always decreasing. So exponential functions are always increasing from left to right or always decreasing from left to right, which means you can't have a negative base. You can put anything you want in it for the domain. The domain is all real numbers. The range of f is any positive real number from a to infinity. So as an example, if a, let me see, I don't know what that is. I don't know what that is. I got this new software and I'm figuring it out as I make these videos, and that was kind of interesting, but not what I wanted. So let's let a equal 5, and let's let b equal 2. So if we have f of, say, 0, we're going to have 5, 2 to the 0, which is just 5. If we do f of negative 2, this is going to be 5 multiplied by 2 raised to the negative 2, which is 5 multiplied by 1/4, which is 5 over 4, which is 1.25. So we are decreasing. However, as we're going left, right now, even if I put in, say, f of negative 5, we're going to get 5 multiplied by 2 raised to the negative 5, which is the same thing as 5 multiplied by 1 over 2 to the 5th, which is 5 over 32, less than 1 but still greater than 0. So your range of this is still going to go from 0 to infinity for this one. So it's going to look something like this. It's going to cross at 0, 5, but it's going to look like this. It's going to just grow faster than when my a is 1. Now what happens when I put in a negative? So, okay, let's do when a is negative 5 and b is still 2. We have f of 0. This is going to be negative 5 multiplied by 2 raised to the 0, which is negative 5. Okay, that's cool. Let's do f of negative 2. This is going to be negative 2 multiplied by 2 raised to the negative 2. Negative 5 multiplied by 2 raised to the negative 2, which is negative 5 multiplied by 1 over 4, which is negative 5 over 4, which is equal to the negative 1.25. If I do f of negative 5, this is negative 5 multiplied by 2 raised to the negative 5, which is negative 5 over 1 over 32, which is still negative 5 over 32. So we know when a is a negative number, what that does is it reflects our graph over the x-axis, and so it's going to look something like this. This is going to go through 0, negative 5, and so this range, when I have f, we'll call this f of x, which is equal to negative 5 times 2 to the x. This range will go from negative infinity to 0, but we'll never get to 0. And this range, which we called f of x, which is 5 multiplied by 2 to the x, you can see that in this case, we have a reflection over the x-axis. So we start at negative infinity and go to 0 for the range. And on this one, we start at 0 and go to infinity. So this coefficient multiplier out front does the same thing as what we expect way back when we learned transformations of graphs, which if it's negative, it reflects over the x-axis, and it alters our range. And it also changes the location in which our exponential function crosses the y-axis. The y-intercept is 0a, always 0a, regardless of what it is. And the horizontal asymptote is y equals 0, unless we have a movement, a transformation, as a vertical shift up or down. And this will always be true as long as we don't have a horizontal shift left or right. The base needs to be positive. We talked about that. If the base is greater than 1, do you think the exponential growth or decay, and how do you know? Well, let's take a look. Let's do f of x is equal to, again, we're going to do 5 times 2 to the x. And since we've done this a couple of times, we know the graph is going to look something like this. It's going to cross right here at 0, 5. And so we know as we read this graph from left to right, it's increasing. Now what happens when the base is 1/2? So let's do g of x, which is equal to 5 multiplied by 2, 1/2 raised to the x. Well, this is the same thing as 5 multiplied by 2 raised to the negative x, because we have this rule that if I have some b raised to a negative number, this is 1 over b raised to the n. So if b is a fraction between 0 and 1, it's actually, since we've been working with that one too, it's going to be decreasing from left to right. It's going to look something like that. It's still going to cross in this case at 0, 5. So we know that the base, if the base is a fraction between 0 and 1, or if the base is bigger than 1, is going to determine whether or not it's increasing and decreasing. Now again, this coefficient out front is going to tell us whether or not we reflect. And then you're thinking, okay, what happens when we mix these two up? What happens if I have, say, we'll go f of x, which is negative 5 multiplied by 2 raised to the negative x. Then what happens? Well, let's go through some of these. So let's do f of negative 2. This is going to be negative 5 multiplied by 2 raised to the negative 2. So this is going to be negative 5 multiplied by 2 to the 4th. Excuse me, 2 squared. I wanted to say 2 to the 4th. It's actually 2 squared. 2 squared, which actually gives me negative 20. Okay. Let's do f of negative 1. This is going to be negative 5 to negative 1, which is negative 5 times 2 to the positive 1, which is negative 10. What about f of 0? Well, we know that this is just going to be negative 5 because we've been messing with that one for a while. F of 1 is going to be negative 5 multiplied by 2 raised to the negative 1, which is going to be negative 5 multiplied by 1/2. So let's start graphing this. So we still go through the 0, negative 5. When I put in negative 2, I'm going to be way down here. So it was negative 20. When I put in negative 1, I had negative 10, so somewhere around there, not drawn to scale. And then it's going to look like this. So this would be the graph of f of x is equal to negative 5 times 2 raised to the negative x. And you can see in this case, because we have a reflection, we have two reflections actually. We have a reflection over the x-axis, and this negative does a reflection over the y-axis from the original graph. So if I would have said g of x is the original graph, which is 5 times 2 to the x, that first we have a reflection, because here's my g graph, which should look like that. We have a reflection over the x-axis, which is this. And the reflection over the x-axis would have done something like that. And then we have a double negative, so we have this negative on the x, and that's why we have a reflection this way. So we had a double reflection, both over the x and the y, if our original graph was 5 times 2 to the x. All right, let's go over here. So the next part here, I know this is not graphing, but it does help to explain how exponential functions actually relate by looking at some of the graphs. So determine whether the equation represents an exponential growth, decay, or neither, and explain why, and then evaluate. So if my base is a number bigger than 1, and my exponent, I have a positive x here, it's not minus x, it's not a negative x, we know this is a growth because the exponential here, the base is bigger than 1, and this is not negative x, so we don't have a reflection over the y-axis, and so we know this is a growth. And so I would get my calculator out, and if I do f of 3, this is going to be equal to 220 multiplied by 1.06 raised to the 3rd power. So I'm going to get my graph out and tell you what that is. This equals 262.02352. But it is exponential, and it is growing as x goes to infinity. This is going to continue to grow. If we look at b, this is not an exponential. First of all, because my variable is not the exponent, and second of all, I don't have a base. I do, the base is 1 plus 1 over x, but this is not an exponential function, because an exponential function, if you recall from just a moment ago, f of x has to be a times b raised to the x, where b cannot be 0, or it cannot be 1. Erase that. B cannot be 1. Oh, what the hell? Give me just a moment. What the hell that was all about? B cannot be 1, and b has to be greater than 0. So, there you go. Can't be 0, can't be 1. It's not in that form. I can still evaluate it, though. I can say f of x or y is equal to 365, 1 plus 1 over 4 raised to the 5th. Let me get my calculator out for that. So put 365 in, 1 plus 1/4. I'm going to raise that to the 5th power. And I end up with 1,113 and 89.16, and I'll go stop there. Now what about the next one? So this is, yes, exponential, and it is growing. So it's increasing. This is no, not exponential. And then this one is of this form, so we know yes, this is exponential. And my base happens to be less than 1, so we are decreasing as x moves from negative to positive infinity. And so f of 10 would be, or y is equal to, 117, 0.97. And this is a check for myself. Since I know it's decreasing, I expect my answer to be less than 117 because that's my initial amount. So I'm going to put 117 in times 0.97. I'm going to raise it to a power of 10. And I get 86. 86 point. So I get 86. I put 9. 86.2786 and some change. So just by looking at the structure of the function, I can tell you whether it's increasing or decreasing and if it's exponential or not. So now we're going to use this table to determine if it is exponential, linear, or neither. So what I'm going to be looking for is basically, I want it to be in this form. I want f of x is equal to a b raised to the x. I want it in that form. And what I'm expecting to do is I'm expecting this to increase or decrease by the same amount. Now, one of the things you can do is you can look at the ratio between terms. And you're like, what? Well, exponentials have to follow the same ratio between terms. So remember, we talked about how the growth has to be the same as we move on, but the rate is not. So I'm not going to do a slope, I'm going to do a ratio. I'm going to take this 40 and divide it by 70, and I'm going to check to see if that's the same thing as this 10 divided by 40. If the answer is yes, then it is. If the answer is no, then it's not. So you can see that, 4 divided by 7 is not the same as 1 divided by 4. 40 divided by 70 is not the same as 10 divided by 40. So the answer is no, this one is not. Let's take a look at the next one. 49 divided by 70, does that give me the same ratio of 34.3 divided by 49? Well, the answer is yes. It actually is 0.7. So this one is a yes. This one was a no. Because that ratio, because we know that exponential functions have to have the same rate percent increase. So the ratios have to be maintained between terms. All right, so find the exponential function given the graph of an exponential function, write its equation. Identify the 2 points on the graph. Boom. If one point of the data is the y-intercept, then we know the initial value. Oh, look at that. Look at that. So we know a happens to be 6. That's nice. Using a, substitute the second point into the equation. So we have f of x is equal to 6 b to the x. And then all I have to do is put the second point in. So I have f of 3 is equal to 6 multiplied by b raised to the raised to the third, which is equal to 750. All right, so b to the third must be 750 divided by 6. So then b must be the cube root of 750 divided by 6. Get my calculator out for that. So just give me a moment to type that into my calculator. And I get 5. So my function is f of x is equal to b, which is 6, multiplied by 5 raised to the x. That's not too bad. Let's take a look at the next one. The next one is I'm given 2 ordered pairs. So I'm going to go back up here to the directions that says if neither of the point is of the form of 0a, then substitute both points into the 2 and then build 2 equations of the form f of x is equal to a b to the x and solve the resulting system. All right? So we have f of x is equal to AB raised to the x. I'm going to just call this y, because here's my x and here's my y. So my first equation is AB raised to the negative 2 is equal to 6. Then my second equation is AB raised to the 3 is equal to 1. So this is A1 over B squared is equal to 6. And the rule I'm using to have done this is if I have a to the n, negative n, this is 1 over a to the positive exponent. So now I'm going to multiply both sides by b squared, and I get a is equal to 6b squared. Cool. I'm going to put that in right here. So I have 6b squared multiplied by b cubed is equal to 1. So I have 6b to the 5th is equal to 1. And the rule that has allowed me to do that is if I have a to the m multiplied by a to the n, this is a to the m plus n. So I added exponents. So then b to the 5th must be 1 over 6, divided on both sides by 6. So then b must be the 5th root of 1 over 6. Okay. I'm just going to rewrite this just a little bit. I'm going to use this rule that says if I have the nth root of a, this is a raised to the 1 over n. So I'm just going to rewrite this as 1/6 raised to the 1 over 5. And then I have this other rule that says, hey, you know what? If I have a over b raised to the n, this becomes a to the n over b to the n. So I can write this as 1 raised to the 1/5, which is just 1. So I'm just going to write this as just 1. And then I have 6, I wrote a b. I have 6 raised to the 1/5. But if I reverse the 1 over a to the n is equal to a raised to the negative n, then this just gives me 6 raised to the negative 1/5. So now I found my b. Once I find my b, I can put that back into my a. So a is equal to 6 times b squared, which in this case happens to be 6 multiplied by 6 raised to the 1/5 squared. I'm using this power to power rule. If I have a to the n multiplied by m, this is a to the n multiplied by n. So this is going to be 6 multiplied by 6 raised to the negative 2/5. Using that rule right here, that I know that that is just going to be 1 minus 2/5, which gives me 6 raised to the 3/5. So now I have found my a. I had my b, so my function f of x is 6 raised to the 3/5, that's my a, multiplied by 6 raised to the negative 1/5, that's my b, raised to the x. And you're asking me, can I clean this up? Absolutely. You're like, what do you mean clean this up? Well, algebraically, this is the same thing as 6 raised to the 3/5 multiplied by 6 raised to the negative x over 5. Now the bases are the same. I can rewrite this as 6, 3 over 5 minus x over 5. And you're like, how is this helping me? Well, here's the deal. If I factor out a negative 1/5, I'm going to have x minus 3, and then I can see the transformations that happen. You're like, transformations again, I'm so excited. Yes, transformations will happen. Let's take a look at this last example here. So I'm just going to erase some of this so I can get this last example. And again, I'm going to do the same kind of thing. I'm going to build two equations. The first equation, this is x, this is y. I have a b raised to the negative 1 is 3/2. My second equation is a b raised to the 3 is equal to 24. A multiplied by 1 over b is 3/2. So A is equal to 3/2 multiplied by B. Put that in right here. So I have 3/2 multiplied by B is my replacement for A. And I have B cubed is equal to 24. So 3/2 B to the 4th is equal to 24. So I'm going to multiply both sides by the reciprocal of 2/3. 2/3. And I have B to the 4th is equal to, well, this is going to cancel to give me 8. This is going to give me 16. So B is the 4th root of 16, which is much lovelier than my last example. Let me just erase this from my last example, which was a lot of joy and fun and deliciousness. So B is equal to 2. We like that. So once we find B, I can put it in right here and I can find my A. So A is equal to 3/2 multiplied by my B, which is 2. So this tells me my A happens to be 3. Much nicer function, f of x, which is equal to 3, 2 raised to the x. Much nicer than the one we just had. Now, compound interest and the number E. So the amount of money, A, the principal P will grow after t years at a rate of R in decimal form is compounded n times per year is given by this formula. This is compound interest. So the number of times that you compound it in a year, the number of years that you do this, and R being the rate as a decimal. If the principal is continuously compounded, then this equation, which is A is equal to P raised to the NT, this thing ends up becoming PE, the principal times this number E raised to the RT. And you're like, what? Well, E is a number, 2.1. So if you take this piece right here and 1 plus 1 over n raised to the NT, as you're compounding as n goes to infinity, this thing approximately equals E, which is approximately equal to 2.718, approximately. It's a number like pi. So here is the formula for compound interest, where you have a certain number of compoundings per time unit, usually time unit being years. So once a month, once a day, something like that. But if the compounding is all the time, every second, every millisecond of every day, then it ends up becoming the principal E raised to the NT, RT, where R is a decimal. This is Leonard Euler, it's pronounced Euler, named this number E, and it is like pi. It does not repeat, it does not, and it goes forever. So this is what we say is the number E, and it's a special base, and it happens when we have a continuous compounding, where we have P as the principal, E raised to the RT. So this is the graph here, where the exponent is a positive x, and here it is where the exponent is a negative x. We still go through 0, 1. It's just the number E is 2.772-ish. So it's going to grow faster than 2. It's going to grow slower than 3 because it's bigger. The base being 2 is, or the base being 2.72 is bigger than 2 but less than 3. So it's going to grow between those two. What does that mean for us? Well, we know that this is how we do continuous growth or decay. So A is the initial value. If we have an R that is positive, then it's going to grow. If R is negative, it's going to decrease. So this takes on a lot of applications in business. It also takes on applications of bacterial growth and decay because it's always growing or it's always decaying for bacteria. So if I get my calculator out, and I should have an E button on my calculator, and with that E button on my calculator, I can do an approximation, because these are always approximations. And we know this is 2 point, and it's 4 decimal places. The first one's going to be easy. It's just going to be 2 point. Let me get my calculator out. So I have E, which is 2.7 2 each, but 718.3 to 4 decimal places. E raised to the third is about, well, more than, because it's not quite 3 cubed, but it's less than 2 cubed. It's approximately 20.0855. E raised to the negative 0.4 is 0.6703. E squared is going to be bigger than 4, but less than 9. So we get 7.3891. All right, so we have that on your calculator. And if you don't have that on your calculator, you can use 2.72 each, because that's what it's approximately equal to, 2 decimal places. If we're asked to evaluate, we've been doing a lot of evaluation, so this should be pretty straightforward. If I want f of negative 3, this is just going to be 2 times 5 raised to the negative third, which is 2 times 1 over 5 to the third, which is 2 divided by 125. If I do f of negative 1, this is negative 4, 2 multiplied by negative 1 plus 3, which is negative 4, negative 2 plus 3, which is negative 4 raised to the 1, so it's just negative 4. F of 2, this is negative 3 over 2, multiplied by 3 raised to the negative 2, plus 3 over 2. This is negative 3 over 2 multiplied by 1 over 3 squared plus 3 over 2. This becomes negative 3 over 2 multiplied by 1 over 9 plus 3 over 2. But this reduces to 3, so I really have 1/6, negative 1/6 plus 3 over 2. Common denominator here is 12, so negative 1/6. Common denominator is 6. So negative 1/6 plus, multiply this by 3 and this by 3, plus 9 over 6. So I get 8 over 6, and this reduces to 4 over 3. And those are my answers. It says to round, but yeah, I didn't have a calculator that's quick. Okay, here's my application. I have a couple of applications. And it says, suppose the 100,000 is invested at 6.5 interest compounded semi-annually. Is this continuous? And the answer is no. Semi-annually means it's happening twice a year. So my A of t, which is the P1 plus R over N raised to the NT. My principal amount is 100,000. 1 plus my rate as a decimal, 0.065. Number of times a year it happens is twice, and then we have 2t. So I can clean this up just a little bit, and I'm going to have 100,000. 1 plus the 0.065 is 1.0325 raised to the 2t. So if I want to know what it's like at t is equal to 0, I'm going to do A of 0, which we know is the initial amount, which is the 100. A of 4, A of 8, and A of 10 is going to be using this formula over here. I'm just going to put in 4, 8, and 10. When I put in 4, I'm going to get $113,647.59. When I put in 8, so I let it run for 8 years, I have 129,000 man, that was difficult. 129,157.75. And then when I put in 10, so if I let this run for 10 years, I have $137,689.43. So if I put this into account that is continuously compounded at 6.5% interest, in 10 years I will have made $37,000 doing nothing. But you know, I'm a teacher, so I don't have 100,000. But if you have 100,000, you could do this. All right. The number of foreign students studying in a high school in the United States grew from 6,541 in 2007 to 65,452 in 2012. This came from the Council of Standards of International Travel. Would this be modeled by continuous compounding? It would be modeled n times per year. Well, so we are assuming that it doesn't happen once a year. Like the students who come in to study don't happen once a year, September 31st of every year. It just doesn't happen. So we're going to assume that this is continuously compounding. So we have to find an equation. So we're going to use the first set of numbers, which is going to do 6, 5, 4, 1, and in year 0. So that is actually the output. So at year 0, I have 6,541. And you're like, how do I know that? Well, because it's the year is independent, and then the number of students we have there is dependent on the year that we're talking about. It's not, hey, tell me the students, and I can tell you the year. It is tell me the year, and then I can tell you the number of students that came in. So this tells me that this must be my A value. That's nice. Now, if I consider 2007 as being year 1 or year 0, so the initial amount, then I just need to know that if I have 2012 minus 2007, that is my input, which is going to be 5. So that is my ordered pair input, which is 5, 65,452. And remember, we needed that because we needed the ordered pair. And so we have my f of x, or t if you want to use t, is equal to 6,541 b raised to the x. My output is 65,452, 6,541, when I have b raised to the 5th. So I'm going to divide both sides by the 6,541, so I'm going to have b is equal to the 5th root of 65,452 divided by 6,541, and put that in my calculator, and I get b is equal to 1.5851. Go about to 4 decimal places for these. So my function f of x is equal to 6541, 1.5851 raised to the x. Now, from 2007 to 2017 is 10. So using this f of 10 is going to be 6541 multiplied by 1.5851 raised to the 10th power. And when I do that, I get 654,955, because it actually was 54 point some change. And because these are people, we always round up. So that, if that was a valid model, that's actually a huge growth. That's it for this video, and we will see you in class.